So we have seen the condition monitoring processes. Now we want to look at vibration analysis proper. So in this section, we are going to look at what vibration is, how we can gather vibration information and carry out the analysis. So we want to enhance your understanding of what vibration is and vibration analysis. We are going to look at the fundamentals of vibration, that is to bring you up to speed for you to appreciate the basics of vibration and vibration analysis. Then how we carry out vibration measurements to collect this vibration information from the field, from our equipment in the plant. Okay. So we are going to look at all of that, where on the equipment, the position that we need to carry out those vibration monitoring or gather such information from in the plant. We are going to look at all of those. Then, of course, the analysis method, the various methods that we can use to analyze the information that we gather from the field, so that we'll be able to deduce or infer what is actually wrong with our equipment. Then, of course, we'll look at the common faults on the equipment and how you can use the information you gleaned or gathered from the vibration monitoring and analysis to determine these common faults, that is their signature in vibration, that is their vibration signature. Then we'll look at some case studies to conclude this section on vibration analysis. So let's dive into it. So what is vibration? What is vibration? Okay. So as you go through the plant, as you go through your plant, what do you hear? So as you hear this sound, is it noise that you are hearing? Of course, it is not noise. It is your equipment speaking to you. So it's not left for you to understand the language that your equipment is speaking. And that comes in the form of this vibration and the noise that you are hearing. So how do you analyze this noise, so to say, to give you useful information that you can use in determining the condition or the wellness of your plant equipment? So now, vibration, as you well know, is the movement, okay, to and fro movement of a particle about a main position, as you can see on your screen. So if this is the particle under consideration, okay, the to and fro movement of that particle about this main position is the vibration of that particle. So when an equipment is working, okay, every part of the body is actually vibrating. So the particles on those parts, they are actually moving to and fro about a main position. So that is the vibration we are talking about. So as you can see here now, okay, so as this equipment is working, it is causing the component parts of this particular equipment to be vibrating, or the particles of these parts to be moving about their main position. So what this goes to tell us is that a normally working equipment has its own normal vibrating or vibration signature or vibration level. Okay, so that's why we said when you go through the plant, what do you hear? Is it noise, or you hear your equipment speaking to you? Of course, the operators and the maintenance personnel, they've gone through plant and noticed change in the sound from a particular equipment, and from that they could say that that equipment is about to malfunction. And of course, they will tend to want to do what they can to restore or to remove that abnormal sound that they are hearing from the equipment. So vibration is the to and fro movement of a body or a particle about a main position. Okay, so this to and fro movement, as you can see, can be extrapolated to give you this waveform, sinusoidal waveform that you are seeing. Okay, so this is pure vibration, but in real life situation, the waveform is not as smooth or as sinusoidal as you are seeing on the screen. So we will know the reason why it is like that as we go along. So there are some basic concepts that we want to also remind ourselves of, because we are going to be using them during our vibration information gathering, data analysis, and trying to deduce what is actually happening with with our equipment. All of this we should know. So the amplitude, which is the maximum height, okay, of that vibrating particle above the main position. Are you getting it? So this is the vibrating particle, okay. The maximum height it will get to, as you can see here, above this main position, which is from here to here, gives you the amplitude of that vibrating particle. Are we getting it? Then the frequency of vibration, which is the number of this circle, okay, that you can get from that vibrating particle per unit, that is per second, is the frequency of the vibration. Then the phase is actually telling us about the position of this particle, okay, with reference to this zero position. Are you getting it? So if it is say 90-degree, as you can see here, okay, and the position of it, if it is 90 degrees, it should be somewhere here. Sorry, if it is 90 degrees, somewhere here. If it is 180 degrees, somewhere here. 270 degree here, and then 360 degree. Are we getting it? So which means that 0 and 360 are in phase. So as it's moving to 90, you see that here will be the position of the particle at that particular point in time. So you can trace the position backward, okay, which is here, this particular position, that's 90. Then here, which is here, is 270. Are we getting it? So the phase is the relative position of the particle, okay, that is vibrating. So we have seen the frequencies. Then still on the fundamentals, things that we need to know, because these are what will determine the measurement units, okay. So we've talked about the amplitude of vibration, which is the maximum height from. So at times we look at the average of this amplitude, because like we said earlier, the vibration may not be as smooth as we saw earlier, okay. The waveform may not be as sinusoidal as this. So what do we need to do when the amplitude vary with time? Okay, we can average them and take the average of that amplitude. So the best average that we can take is the root mean square value. So which means that the sample data, we square each of these sample data, add them together, take the mean of that squared and added a sample, okay. Then we take the root, okay. That is the root mean square value of the sampled data. So what this means is that, assuming we have 3 samples from our vibration information, the vibration information that we collected over a particular unit time, let's say per second, okay, we were able to get 3 samples. So assuming these 3 samples, they are say 5, 8, and 9. 5, 8, and 9. So to get the root mean square value, you square each of these. That is the square of 5, square of 8, and square of 9. Add them together. Okay, so the sum of that square is what you now look for its average. That is, divide by 3. So what will result from the division by 3 is what you will now look for its root. That will now give us the RMS value. Okay, so though the computer within the instrument will do it automatically for us if we are looking at the root mean square value. So then the next is the peak to peak. So remember, in any wave that we have the negative peak and the positive peak, okay, which is the crest and the trough. Okay, so the distance between the trough, that is the negative peak, and the crest, the positive peak, becomes the peak to peak. Are we getting it? Becomes the peak to peak. Okay, so this shows the formula for the calculation of the root mean square value. So the probe, as you are collecting the information, the vibration measurement equipment will be giving a direct reading, either a root mean square value, amplitude in mils or millimeter, okay, and then the peak to peak value in also millimeter. Okay, so this now becomes the measurement unit for our amplitude. And remember that when we go with handheld vibration instrument into the plant, what we get from that instrument is the overall vibration and is the amplitude of vibration, okay, of the particle on that spot where we are taking the reading. So that brings us to the first measurement unit, which is displacement. Okay, displacement, which is the normal displacement in your equation of motion, the distance moved. Okay, but in this case now, we are looking at the distance traveled. Okay, the maximum displacement is the amplitude, the distance traveled by that vibrating particle from the rest position or the mean position to the maximum or the peak of the wave. Okay, so that becomes the displacement from this main position. So we have different units, as we can see later, that you can use to represent this displacement. Then we also have velocity, okay, which is the rate of change of this displacement per unit time. Okay, so the displacement, we can get like we said earlier, the vibration amplitude of the particle, while the velocity will give us more information about those low frequency events that, as we'll see later. Okay, so and the unit is usually the displacement per unit, that is per second. So if our displacement is in millimeter or mils, okay, it will become millimeter per second. So we also have the acceleration, and we have, as we'll see later also, transducers or sensors that helps us to collect the acceleration information. Okay, because it is usually the rate of change of velocity, which is displacement per unit time, the square of the unit time. Okay, so which is millimeter per second square. So the acceleration, the sensor for it is the accelerometer. So the accelerometer gathers the information, mostly those high frequency information, and we'll see the use for them as we go along. So here is a summary of all that we have been saying. So here are the units, okay, that could be used to represent the displacement measurement. We have the millimeter, we have the micrometer or micron, okay. Then the velocity, we have the millimeter per second. The acceleration, we also have millimeter per second, meter per second, millimeter per second square, meter per second square, centimeter per second square, or the GAR, okay. So these are some of the units that you will come across during the course of your vibration analysis. So here are definition of some of the units too. Micrometer or micron is the unit for measuring displacement, especially for small vibrations. Okay, millimeters, they are used for larger vibrations. Then the velocity, which is usually a common unit, okay, for velocity measurements. They are for low frequency vibrations, like we said earlier, okay. Then we have the micrometer per second or micron per second, okay, and that is used for high frequency vibration. Are we getting it? But velocity generally, if you take your velocity probe, that means you are basically looking at low frequency. It will give you better information, though it will capture high frequency vibration, but it will give you better information about all the low frequency vibrations. So we have the acceleration, okay, and basically we use it to, though it will also, like in the case of velocity, capture low frequency vibration, but it will give us better information about the high frequency vibration. So all of these parameters, we are seeing the SI units that we can use. So when you come across them, you know what you are actually talking about. So here are the physical example of the accelerometer, okay, or vibration sensor. And you see that they are placed on the bearing housing, okay. So the orientation or the direction of measurement, it is usually such that we'll get the most information from that housing. So as you can see on this diagram, so we have the driver, which is an electric motor, and then the driven equipment, your load, which is the pump. So you see we have the non-drive end, which is the hardboard end of the electric motor. Okay, so this is the inboard, okay, which is this, where you have the coupling, and that is what we have here. So this is the inboard end of the motor. The other end of the motor, okay, at the back, is the outboard end of the motor. So we have the inboard for motor, we have the inboard for your pump, and the outboard for your pump. So we take vibration reading on each of these bearing housing in 3 axes, okay. We take on the axial axis, that is the axis that is parallel to the shaft axis, okay, or the axis of operation, the turning axis of the bearing that we are looking at. So any direction that is parallel to it becomes the axial direction. Okay, so like in this inboard end of this motor, we know the bearing is here. So since the coupling is here, we cannot really access the axial direction directly. So but we can use this spot, okay, placing our probe directly into the spot. Okay, as you see this probe now, this base, we attach it to this end so that the probe will be parallel to this coupling, okay, making the direction parallel to the direction of the shaft, the parallel to the shaft in the electric motor. So that becomes our axial direction. So we can take it from the outboard. This one is clear enough. We can take it from the inboard in this case too, because the coupling is protected, is shielded. Okay, so there is no safety implication as in this case. So we also have other two directions, the horizontal direction, okay, which is the this direction that you are seeing here, where this you have this probe. This is the horizontal direction to the bearing, and then we have the vertical direction, which is this vertical direction. That is the orientation of this particular probe as you are seeing it. It is placed on the vertical axis to this bearing, okay, that you are looking at. So these are the three orientations: the outboard axial, outboard horizontal, outboard vertical, that you take the vibration information on the electric motor outboard end, okay, that is the non-drive end. Then on the drive end, you take the inboard vertical, which is the same thing, the same orientation like this, because you place it on top. Then the inboard, this is the inboard anyway, the inboard horizontal, okay, you place it on the horizontal axis, that is the x axis to the bearing. So if this coupling is shielded, as we have in this case, it means that we can also do the axial direction without any safety implication. So we have for the pump also, the inboard vertical is the same thing, the orientation, outboard horizontal and outboard vertical and outboard axial, okay. So in a single equipment, a complete pump train like this, it means that we will take at least, we have at least 1, 2, 3, 4, 5, at least 10 vibration information. That is at least 2 from each bearing, and we have 2 bearings on the motor, 2 bearings on the pump, okay. So we'll take at least 10 vibration, between 8 and 10 vibration information, okay. So still on the fundamentals of vibration. So as you can see on this motor, we can take here vertical. If there is no space, we look for the closest position that we can take that horizontal information. It's just for us, or for you, to know precisely what you are doing. So as you are collecting that vibration information, you see that that to and fro movement of that, the particles at that position where you have the probe, will be converted into sinusoidal waveform or waveform, okay, as we saw earlier. But remember, the components of this equipment have more than one particle. Are we getting it? So since it's having more than one particle, that means there is every tendency, or it has more than one particle vibrating, because we have different forcing functions, okay. So there is that tendency of having more than one wave sources, and these waves, they are coming at the same time. So which means that both of them, as they are coming, they will be superimposed on one another, because we may have them multiple, in some cases in tens, in hundreds, okay. So remember, we said earlier that the waveform is not always sinusoidal. It is sinusoidal because we are considering the vibration of just a single particle. But once we have so many vibrating sources, okay, you see that the waveform that will come at the end of the day will be distorted, as you see here. So the more forcing function, or the more vibration source that you have, the more distorted this waveform will be. Okay, so in real life, this is close to what you see. Some are even worse than this. Are we getting it? So this is the waveform and this is the mean position. So you see that we have both negative peaks and positive peaks. Okay, but the beauty of it is that a trained eye can see that there is a pattern in this waveform. Are we getting it? Though to the untrained eye, it could be something close to rubbish. Okay, but if you look at it, you see that we have regular pattern. Are you seeing it? So all of these patterns, they correspond to some major forcing function of vibration sources. Okay, so this interval, the time, see, here is the time between here and here. If you kind of compare it with the rotating speed of the equipment, that will give you an idea as to where the impact or the vibration is coming from. Let's assume that this space is 1 times RPM. Okay, as we'll see later, one of the major events that can result to such 1 time RPM event is unbalance. Okay, so that will tell us that it is happening once in every revolution of the shaft. So that will give us an idea as to what is actually happening. So this is what you will definitely see in real life. So it will make little or no sense. Okay, apart from the vibration amplitude, the overall vibration that you can actually glean from this, that will tell you that the vibration is increasing beyond, okay, by merely looking at the amplitude here. So if it is increasing, you will know that it is something is amiss. Okay, something is contributing more than what is normal. So we'll see how that can make sense to us later. Like we said in the earlier section, fast Fourier transformation can be carried out on this waveform, okay, to convert this information into the frequency spectrum, okay, or the vibration spectrum. So in so doing, as we'll see later, we will now be able to isolate the individual forcing function, and it becomes very clear to us which part of the vibrating source or the equipment is contributing the vibration to the overall vibration that we are looking at. So we are still on it. Like we said before, the frequency spectrum, since we can get little information from this vibration waveform, we'll now carry out what is called fast Fourier transformation. Though that is done, okay, is a mathematical analysis. It is done automatically by the analyzer, the equipment. So it will carry fast Fourier transformation on this waveform and convert it into frequency. So what it does is that each of the vibration that is coming from a different source, this is the overall vibration, okay, which is something like this complex vibration that you are seeing, that is almost meaningless. So all the vibration that are in the waveform that are superimposed to give you this, it will now separate them into the individual vibrations. Are you getting it? So in this case, we have 3 vibrations sources or waveform superimposed to give us this complex waveform. Let's assume that what we have here is this. So we have been able to isolate all of them now. Okay, so as we isolate them, the fast Fourier transformation will tell us at which frequency is this vibration happening, at which frequency is this vibration happening, and at which frequency is this vibration happening. And that is what we are seeing here. So you see the peak at the frequency. This axis is the frequency axis. Remember, here we have amplitude against time. Then here we have the frequency axis. So each of these forcing function, they actually occur at a particular frequency of vibration. So that will help us to zero in on the cause or causes of the problem. So this is what you get at the end of the day after carrying out fast Fourier transformation on the vibration wave form. So you see that all of these peaks, they are happening at different frequencies. So later, we will also see that different fault conditions on rotating equipment, they happen or they occur at different frequencies. So that will help us to actually determine what is causing the problem or the high vibration. So what we are doing in essence now is analyzing the information that we collected from the field, okay? As you can see on the screen. So we've talked about the accelerometers, the velocity transducers, and displacement transducers. Okay, so when you want to collect amplitude information, one-off vibration events, and what have you, the displacement transducers will give you good information. Like most of the handheld that you have, most of the transducers in them, they are displacement transducers, those handheld vibration meters. Then on the analyzers, okay, the velocity transducers, like we said earlier, they are good for getting information or gathering information about low frequency events. So there are some fault conditions that happens in the low frequency range of the spectrum, okay? As we'll see later, like if a fault condition like misalignment, like unbalance, looseness, and what have you, all of those, they happen in the low frequency range. The velocity transducers can help us to get information in that area. Then the accelerometers, they assist us also in getting information on the high frequency range. So bearing problems, gearbox problems, as we'll see later. In fact, all high frequency events, okay, the accelerometer will better capture it for us. So this is an example of an accelerometer, okay. So that is a vibration sensor, which could be displacement transducer, an accelerometer, or so it depends on the information that you want. That will determine the kind of probe that you will order for, okay, or that you will use, so that you're able to get the information that you actually need. So with this, you go out to carry out your vibration information. Remember, on each bearing housing, you have the vertical, the horizontal, and the axial direction, as we discussed earlier. On the motor too, the inboard end, the outboard end, you have those orientation, okay, those axes to collect vibration information from. So this is your vibration analyzer. So this is the vibration analyzer, okay. So and this is the vibration probe, okay, or transducer, which could be an accelerometer that you place. The base is magnetic, so as you place it on the bearing housing, it attach, okay, it magnetize the housing and get attached itself, attached to the housing on the particular spot or direction that you placed it. So as you collect your information by pressing whatever button that you have on the analyzer to collect data, okay, So you can also be looking at the live data, looking at the vibration as you are measuring it, looking at the waveform and also the spectrum, okay? And you will see them live as it's changing with time. So here we have the accelerometer. You see, as you place it on that particular position, so the to and fro movement of the particles on that position will now be converted to the electrical signal, okay, that will be recorded by the analyzer or the handheld vibration meter, okay, as in this case now is a meter, but in this case now is in this particular case we have the analyzer, okay. So you go to the feed, that's on the data acquisition, place it on those positions either in the inboard or the outboard end, okay, and acquire your information. So if it is an online system, you'll see that the transducer will be wired, okay, to the control console. Are you getting it? That will be giving the information straight to the control room. Or else you acquire the information on your analyzer, then you go and dump it into the computer in your office, okay, and further analyze the data that you have collected. So we have discussed this before. These are the orientations, okay, that you can place your probe, as you can see here, okay, to get your vibration information. So we have on the motor, so this is horizontal, axial, vertical, axial, horizontal, okay. This is the inboard end of the pump, outboard end of the pump, okay. Though this is an overhung impeller pump, okay. So both bearings, they are here, okay. So you take the information that you want, the vibration information from here, okay. So this is what we are describing: the vertical direction, the horizontal direction on each bearing, then straight the axial direction, okay, which is this if it is exposed. If not, you can take it here, place the probe straight. So assume that this is your probe, this is the tip of your probe, okay. That is the magnetic end, so you place it straight onto this position as you are seeing on your screen. Then you acquire the data, okay, collect the data. Then after collecting the data, the next stage would be to analyze the information. So the time domain analysis, which is the waveform that we discussed before, or you can trend the information by collecting the overall vibration data, okay. As you trend the information, you will be seeing the trend as it is changing, okay. Or if you are using an analyzer, you can also go into the time domain, which will give us the waveform, as you can see on the analyzer, okay. So if you look at this, you can get some information, though few, minimal, but you can get some information from this, because you see that something is happening at each of these stages, okay. So if, like we said earlier, if it is these intervals, they are equal to the RPM, it could be an impacting event, okay, that corresponds to 1 time RPM, which could probably be as a result of imbalance, okay, or any other 1 time RPM event. Are we getting it? So those are the few things that you can actually glean from the vibration data. So for us to get useful information, we need to carry out FFT, fast Fourier transformation, which will be done automatically by the analyzer. It's just for us to press the frequency spectrum button that automatically converts the waveform information to frequency spectrum. Then we can also do phase analysis, that is the position of the particle, okay, per unit time with respect to a reference point. Are we getting it? So when we do phase analysis on one side of the coupling or across the coupling, that will also give us some information. We can do other analysis or orbit analysis, okay. All of this will give us the information that, or will help us to deduce what is actually wrong with our equipment. So we've talked about time domain analysis, which can give us just limited information, as you can see here, okay. So look at it, you see that something is happening at these intervals, okay. So this can give us an idea. Then the overall vibration level too, you can see it here. So if it is going beyond what is tolerable for that equipment, we will also see it. Are we getting it? Then you can have a baseline waveform information and be comparing, as we said earlier, subsequent vibration waveform to the baseline information, okay. So once there are changes or discrepancies, then that will tell you that something is going wrong. Remember, the baseline information is taken when the equipment is either new or newly overhauled. That is when the equipment is working perfectly or correctly. That's when you take the baseline data or information. So like we said too, the first is trending. So you go to the feed. Each time you go to the feed, you collect information, you plot, okay. As you plot, you'll be seeing the trend as it is changing each time you go. So it is the vibration per unit time, as against time, I mean to say, okay. That is what will now form your trend plot. So as it's changing, so this you can do, like we said earlier, you can do with your handheld vibration meters, okay. As you can see on the screen, this is a handheld vibration information. The probe is on the vertical axis, so which means that you trend for the vertical, trend for horizontal, and then trend for axial direction, okay, both on the inboard and the outboard end of each of these pieces of equipment, so that when the trend is changing, okay, it becomes very visible. That's with the handheld. So if you have low budget for this technology, you can actually use this, okay. So the idea, basically, we discussed the bathtub curve before, is for us to know when we are entering that way out region of the curve, which is between the point of potential failure to the point of failure, okay. So as the bearing is deteriorating, if it is bearing vibration we are looking, so you see that the condition of the asset, okay, will be worsening. Are we getting it? So now between here, between this, within this PF, it is for us to see what maintenance intervention we can do, so that we can bring it back to its normal level, okay, of reliability. So now those handheld, most of them, they come with this chart, okay. So you see the overall vibration reading. So this one is very easy to interpret. So you see we have group 1 equipment and then we have group 2 equipment, as you can see. So the group 1 equipment, they are large equipment between this power range, between 300 kilowatts and 50 megawatts, okay. That's the power range that you use this information for. Then between 15 kilowatts and 300 kilowatts. Okay, these are the information that you use. Are we getting it? So this is the height of the electric motor, then the motor between this height. So now when you go to the feed and get your information, okay, with this handheld meter, what will happen next is for you to compare that information with what you have. Assuming you have 2.5, let me say 2.5 millimeter per second. Okay, if you have 2.5 millimeter per second, that means it falls within this area. Okay, then if your equipment is a rigid type, it means that it falls in this area, which is for newly commissioned area, which means the equipment is trying to bed in. Okay, so for the equipment, if it is within this area, it means that the vibration level is fine. Here is also fine. You have 2.8, it means that the vibration is low. Okay, for rigid equipment. Then for flexible equipment, you see that the vibration is normal, which means that you can use the equipment continuously, no problem. But if the vibration level is going up to 7.1, see, it becomes a warning level, an alarm level. Then once it's anything beyond 11, it's a no-no. Okay, so the equipment should be shut down at this stage, and then you look for what is actually causing it. So for these sizes of motor, here are the range, the same thing too. So you just compare what you collected from the feed with what you have on this vibration monitoring chart, or the chart that came with the instrument that you bought. Okay, so this is very easy to use. Then this is another. Okay, we have different classes of machines here. These are the rotating machines, the rotating standard machines, okay, motor fans, shafts, generators, and what have you. These are their frequencies of operations, okay, and this is the ISO standard that is guiding it, which is the same with what we have earlier. Okay, so this reference chart, we have different classes, about 4 classes. Small machines, 20 horsepower, medium machine, 100 horsepower, then larger machines with rigid foundation, and large machines with soft or flexible foundation. So here are the vibration information, either in inch per second or millimeter per second. So anything between here and here on this class 1 is very satisfactory. Okay, and then here and here is good. But once it is increasing to 7, as you can see here, 7 and above, okay, it becomes alarming, which means that you need to do something. So on the yellow, it is a warning, which is an alarm signal. Here you have to shut down. So also with class 2, this is where you can operate infinitely. This is the region where you know that what you are looking at is perfect. Okay, here is a bit satisfactory, but as you are going to the limit, the highest limit, you know it's time for you to think of what to do. Then beyond the warning range, you shut the equipment down. Are we getting it? So the chart is very easy to use. Then the next thing that we can do is to carry out the fast Fourier transformation on the waveform, okay, that we talked about earlier. So we have discussed this earlier too, okay, which basically is separation of those waveforms that have been interposed to give us this waveform to their various frequency of occurrence. Okay, the various frequencies which they are happening. Remember, we said earlier that you can actually toggle between the waveform and the frequency on the vibration analyzer. In some of these vibration analyzer, you can actually see the waveform and the spectrum at the same time. Okay, and then make a sense right there in the field of what is happening. But for you to do detailed information, you have to dump whatever information that you gather, okay, so that you can compare all the points on a particular machine and then see what is actually wrong with the machine. So this is the waveform, and you see how complex it is from this gearbox. So after fast Fourier transformation, you have the forcing function separated into their individual frequencies. So the major peak is occurring here. So it's now left for us to look at the frequency and look at what forcing function, okay, is actually operating at this frequency. So if it is the bearing frequency, or if it is the jar, okay, here is the jar mesh frequency. Okay, we have bearings here too, which could be contributing to that, for this overall vibration that we are seeing. Okay, so all of this will help us to determine what is actually causing the problem.